All right, so here's what I'd like you to do. Go into Schoology. So in Schoology, you have a new folder called Balanced Forces. Yes?
Why can't adults hear dog whistles?
Because when you're old, your hearing starts to...
Can we test it on you?
What's that? Because there's ringtones that old people like me can't hear.
Really?
Yeah. Well, that, and we tend to ignore things that we don't want to deal with. So, all right. So, anyways, in like that right now, it's driving me nuts. Okay. So, anyways, in your Balanced Forces folder, you've got a few things. Now, this we all did together, the bowling ball motion. And the reading, the forces and force diagram, that was done in place of a video. And I'm going to review it today, but I'm assuming that you guys have all taken a look at it because it's going to be really important for what we're going to do both today and tomorrow before you take a quiz, probably on Monday, over how to draw these force diagrams. But anyways, what I want you to do, click on the drawing force diagrams number 1. And you're going to get this guy right here. What we're going to do is we're going to do the first 4 together, just to make sure that you feel confident in knowing how to do these, and then I'll let you do the rest. And then tomorrow we're going to go at a slightly more complicated version of this. But I want to make sure that you guys know how to draw these force diagrams. Because the big idea behind force diagrams is that they show you all the forces that are acting on an object. So let me pull this up really fast.
Was this really necessary for your chemistry education?
Was what?
For raising your puppy?
What?
How to use a Midwest pet home.
I have no idea.
Direct elimination. Use a notion.
Long story.
I am so confused.
It's okay. All right, so here's what we're going to do. So this is how to draw force diagrams. And I've got a few things that I'm just going to review really fast. So the first thing that we talked about 2 days ago was this whole idea behind Newton's first law of motion. So Newton's first is the law of laziness. Okay? Objects that are at rest, they want to stay at rest. They don't want to change. All right? Objects that are moving in a straight line at a constant speed, they want to keep doing that. All right? So how many of you guys have played golf before? Who are my golfers in here? Okay, you've at least played it?
Yeah.
All right? So you put the golf ball on the tee. When does it move? When you hit it. All right? How many of you have played air hockey? Okay. Air hockey is something that everybody needs to play. Now, the problem in the Spencer household, air hockey is, we want to get an air hockey table, but we probably shouldn't because it will mean the end of my marriage. My wife and I get really, really competitive. And as much as I love her, I will not lose to her. All right? And ever since college, ever since we met, we have had, like, everything can be going great until we see an air hockey table. And then all of a sudden all the smiles go away and you get like the look that I'm gonna just destroy you in this. And we go and we'll play air hockey until there's like bruises. I don't know how many of you get bruises playing air hockey, but I manage to. All right? But the whole idea behind air hockey is that you have this table and it has little holes in it, and when you turn it on, air starts shooting up through the holes. And you have this little puck, and the puck will just kind of float right there, hover, okay? And if it's a good air hockey table, if it's flat enough, it'll just stay there until you hit it, all right? But once you hit it, okay, there's no friction. Okay, that air makes it so it'll just keep going on forever if it didn't hit anything else. But can you get an air hockey puck to spin? Or to curve? I guess that's a better way of. No. You've got to hit it, and it goes in a straight line, and it only changes direction when it either hits one of the edges or it hits the other, like someone else's paddle. Okay? That's Newton's first law of motion. Objects that hockey or that air hockey puck wants to stay hovering unless you force it to. It also wants to keep moving in a constant speed in the same direction unless you force it to change. So this is something that's going to be really important. We've talked about the difference between or how forces affect changes in velocity. So when we think about velocity, what's the two ways that we can change an object's velocity? Simon? What do you mean by increase it or decrease it?
I mean, you can accelerate or decelerate.
Okay, so speed up, slow down. Positive acceleration, negative acceleration. All right. What's the other way that you can change an object's velocity? Remember, this is a scalar quantity. No, it's not. It's a vector. So the two different ways that you can change vectors are by changing its speed or what else? Changing the direction. All right. So if you have an object that's either changing speed or changing direction, you can infer that you have what are called unbalanced forces. If it's not changing speed, or if it's not changing direction, what can you infer about the forces then? They're balanced. All right, so balanced forces mean that it is either staying in one spot, or it's traveling in a straight line at a constant speed, or unbalanced forces mean that it's going to either speed up, slow down, or change direction. And that's going to be really important for what we're about to do next with drawing the force diagrams. We also talked about Newton's third law of motion, the idea that what you do comes right back to you. So for every action, there's going to be an equal and opposite reaction. Or when it comes to forces, that for every force, there's an equal and opposite force. A few things that we've talked about briefly, but it's going to be important for you to know. A force is a push or a pull between two objects. And these are the kind of forces that we're going to be talking about here for the next few weeks. You've got touching forces, like when two objects are touching. The normal force. So a normal force is that force that you read about that's perpendicular to the surface of an object. Friction goes in the opposite direction of an object that's moving. Traction is going in the same object or in the same direction as an object that's moving. Extended forces, those are forces where you have objects that are touching, but they're kind of like at a distance. So you have tension. So that would be like when you have a string or a chain or something like that that is exerting that force. Thrust, drag, buoyancy, lift, those are all different kinds of extended forces. You also have non-contact forces like gravity, electricity, magnetism. Those are all forces that can extend over a space without having objects touch. And some people in YouTube land try to make you think that they do things that they really can't. But that's a story for another day. All right, so that's a review too. You guys need to know how to label these forces. So this is something that you're going to be doing here in a few minutes. So when you're labeling forces, so F stands for force. And then you write it as a subscript. So the first thing you do is write the kind of force that it is, what the force is acting on, and what it's acting by. Does that make sense? Maybe I should put it this way. What's doing it? Yeah, that's a good way of putting it. So, for example, if I wanted to talk about the forces of gravity that's acting on me as I stand right here, you would write that as F with the subscript gravity on Mr. Spencer by the earth. so here's where we're going to start doing this stuff. So we're going to draw what are called force diagrams. And what force diagrams do is they help you identify all of the forces that are acting on an object and be able to use that to figure out why an object moves the way it does. So remember, balanced forces means you have constant velocity. Unbalanced forces mean you have acceleration. You have a change in velocity. So let's do this first one together. So when I first saw this picture, I thought it was a cat sitting on a record. And when I say record, most people don't know. What's that? It is a rug. I thought it was a record, but it's a rug.
Why would a cat sit on that? I think it's a record.
I don't know. That's why so you see why my brain just doesn't work the way normal people's brains work. But let's do this, okay? So what you're going to do is we're going to draw a force diagram. So the very first thing that we do is we have our little picture here. And then the next part, let me find a marker. So this is my system right here. We've got the cat sitting on a rug. We want to identify all of the forces that are acting on the cat as it sits on the rug. We don't care about anything else besides that. So to make life easier, what we are going to do is we're going to say, you know what? I want to make this easy. I'm just going to draw a dot. And that little dot is going to represent the cat. And then I'm going to draw an axis. So we've got the X, the Y, and now I want to identify all of the forces that are acting on this cat. So first question that you ask, is the cat accelerating? No, okay? It's not changing speed, it's not changing direction. So if it's not accelerating, what do we know about the forces? They are balanced, all right? So what forces are acting on the cat? Gravity. Okay, which way is gravity pushing? Down. Down towards the center of the earth. So I have my dot right here. I'm going to draw a line down, and that is going to be the force of gravity on what? On the cat. By what? Earth. So we've got gravity that's pulling down on the cat. What is causing the cat to not go flying through the floor and down to the center of the earth? What's that upwards force of the ground called? Normal force. Okay, so whenever you have an object, and that was in the reading, whenever you have an object that's in contact with a surface, okay, that surface exerts a perpendicular force to that. So kind of like if I go and I decide to punch the wall, okay, I exert a force on that wall, the wall punches me back. That force that the wall punches back with is called the normal force. So if this is not accelerating, how does the normal force compare to the force of gravity? Which way is it pushing? Opposite. And how much is it pushing? Equal amount, but just in the opposite direction. So I'm going to draw a line that's kind of sort of the same length, or at least it's supposed to be. Just in the opposite direction. So we're going to call this force of, or the normal force on the cat by the ground or by the earth, whatever floats your boat. So do you see how they balance out? They're equal and opposite, and that makes sense because it's not accelerating. It's not changing speed. It's not changing direction. That's really easy for objects that are standing still. It gets a little more confusing when you do the next example. And this one I'm going to have you guys do on your own. So we talked about that the total force is 0 because they canceled out. This time, here's what we've got. We're going to play pretend a little bit. We're going to pretend that you've got this skater who is skating along on the ice, and it's frictionless ice. All right, so there's no friction or anything else like that. And she's moving at a constant speed across the ice. What I want you guys to do is work together in a group, and as a group, come up with a force diagram for Skater Lady. All right? On the whiteboards, yes. Okay. Go. All right, guys, so let's talk about this. I saw some, I think a lot of you have the same question, so this is what you should have come up with. And this is where a lot of people get stuck. Because before, with the cat, it was really easy. Let's see. With the cat that was sitting still, it was really easy to say the only forces that are acting on this cat are gravity and the normal force. But, Sam, you having a case of the dropsies today? But with this, it's the exact same situation. All right? She's going, now we're doing a little bit of playing pretend. We're pretending that she's on a frictionless ice surface. We're pretending that she's moving at a constant speed, not changing direction. So as she moves along there, she still has gravity acting on her. She still has the normal force pushing up. But the example that I was using with some of you goes back to the air hockey table. All right? In air hockey, when you turn on the air, and if it's a good table, what does the puck do?
Stay.
It starts to hover, but it stays. When does that change? When you hit it. All right? Now, when I hit it, what does it do? It starts to move. Is that accelerating? Yeah, that's accelerating. Okay, so that means that there's an unbalanced force acting on it. As soon as I stop touching the air hockey puck, does it continue to move? Yeah, it keeps on moving. Is it still accelerating?
Maybe. Nope.
It goes in a straight line at a constant speed. And the only time it slows down is if it hits the wall or if the other person with their paddle hits it. So if it's moving in a straight line at a constant speed, is it accelerating? No. So what does that tell us? If it's not accelerating, what does that tell us about the forces?
There's none. Well, there you go.
That there's either no forces acting on it or it's balanced. So is it possible for things to move when a force isn't acting on it? Mm-hmm. Yeah, and that's the case we have right here, where she's going along in a straight line at a constant speed on this pretend frictionless surface, and even though she's moving, there's not any forces acting on her besides gravity going down and the normal force going up. All right, hand the pen to somebody else. I've got another one for you. Who are my softball players? All right, Cheyenne. Cheyenne, what position do you play? First? Okay. All right, so in this example, we've got one of Cheyenne's playing first, and who do you play against that you guys absolutely hate? Okay, and there's I won't even say the name. All right? You're playing that other team. All right? And one of the girls she's off the base a little bit. She's trying to be sneaky. Who's one of your pitchers? Taylor. Okay? Taylor does a great pickoff move. And you're right there. You're ready for it. The player from the other team who's not that bright All right? She slowly starts to come back and she decides to like slide back towards first base. Draw a force diagram describing somebody who's sliding towards a base. All right, so let's take a look at this. We'll talk here. We'll make sure that everybody's on the same page. So you've got you have the softball player. She's sliding. Is her velocity changing?
Yes.
Yes. Okay, she's slowing down. Okay, so if you are slowing down, speeding up, or changing direction, what does that tell you about the forces? They are unbalanced. So, I still have gravity pointing down. I still have the normal force pointing up. Those cancel each other out. But now I have friction. And why is friction pointing towards the right? Why is that acting towards my other right, the left?
Because eventually she's going to stop. She'll just slide forever. So.
Right, so friction acts in the opposite direction of motion. So that's why friction would be this way. And it's an unbalanced force. Okay? It's causing her to slow down. Now, some people have an arrow going this way, and they're trying to figure out what happened to it. Is that... Now...
We don't need it because it's an unbalanced force, right? You don't need anything.
Well, is it a force that's acting on her? Well, I guess let's back up a step. What is the force that's going this way? It's her acting, it's a friction force acting on the ground by her. So, do you see how all of these, it's on the player, on the player, on the player? That other force is not on the softball player, it's on the ground. So if we were doing one of these on the ground, then we would write that. But for this one, we're not going to. Okay, Evan, did you have a question? No?
No.
So is momentum ever going to be part of what?
Momentum has to do with force, but is not a force. All right, last one. We've got a chandelier. It's suspended from the ceiling by a chain. Draw a force diagram of this one. This is the last one. All right, gang. So let's just looking around. Looks like we've got everything here. Let's compare. You've got the chandelier. It's hanging from that chain. What forces are acting just on the chandelier? You have. So first thing is, remember, we're just talking about the chandelier. So for the chandelier, is it accelerating? Is its velocity changing? No. So we have balanced forces. We know we have gravity that's pulling on the lamp. But what's keeping it from falling? The tension that's in the chain. So the tension is pointed in the opposite direction. All right, equal but opposite. All right, so those are the very basic ones. Tomorrow we're going to go over some more complicated ones. What I'd like you to do is finish up those other questions that are on that sheet. If you need to work on on finishing up your test, we've got not enough time. So we'll do that tomorrow.